The theorem states that order of the group divided by order of the subgroup should be an integer. That is, order of the group should be divisible by order of the subgroup. How do we prove this? Proof is very simple. A group can be written as a subgroup and sum of cosets. Suppose I have some elements A which are not G in H. I can make a coset out of that. Then remaining elements I will get as a coset. Then one more element. So I can write down this as comma G2 times H, etc. some Gm times H. Left cosets or right cosets. Okay. Now, what does it mean? If order of H is equal to some K, this will be M times K. Correct? So, if order of H is equal to some K, then order of G is equal to M times K. Or order of G is equal to M. How many elements will give distinct cosets? How many elements will give distinct cosets? So, in this particular example, how many number of cosets are there? Here, we can write G as H I times H. Minus I times H also give the same thing. Okay, H and I times H. So, I have 2. Total is 4. So, 4 is divisible by 2. Okay. Order of the group is divisible by order of the subgroup. This is called the Lagrange's theorem. So, whole group can be divided into subgroup and its cosets. Now, if you consider a group G such that order of the group is equal to P, a prime number. Let us say consider a group whose order of the group is P and P is a prime number. What can we say about this group? What is the property of a prime number? It is not divisible by any other integer other than 1 and P. That means it cannot have subgroups. That means what? If you have more than one generator, then you can have subgroups. More than one generator, you can have subgroups. It is a cyclic group. So, all groups whose order of the group is a prime number are cyclic groups. It cannot have any subgroups. It can have only trivial subgroups. So, G has to be cyclic group. All groups whose order is prime number are cyclic groups. They have only trivial subgroups, namely identity and full G. No non-trivial subgroup exists. Definitely for these cyclic groups whose order is prime, this property is true. So, this is an application of this theorem. You understand that, right? If there are divisors, then we should have subgroups. Since prime numbers will not have any divisors, it has no subgroups. Yeah. Someone was asking a question. Okay. Now, for understanding the full implication of this, we have to understand the following thing. If GIH and GJH are two cosets, basically they are two left cosets of H in G, then GJH, GIH is equal to GJH, or GIH intersection GJH is an empty set. That means if one element is common, then all elements are common. Otherwise, there are no elements that are common. If you take two cosets, either they are disjoint or they are same. Their intersection either null or the intersection is the full set. Only if we understand this, then we can use this decomposition of the group in terms of subgroup and its cosets. Because I am writing this, but when I write like this, each one is distinct. There is no overlap between this. Okay, so I will leave it for you to prove this. If you have some difficulty, then we can do it in the tutorials. Also, there is another interesting theorem which can be used to verify whether a given subset is a subgroup or not. Normally, you have to show that it is a group, which means you have to show that the elements of H also satisfy all the 4 axioms. Okay? So, a subset H of a group is a subgroup if and only if for every Hi, Hj in H, Hi inverse Hj is also in H. So, you have to just verify this one property. Then you can say that this is a subgroup. So, this is a very interesting theorem. Take all pairs and show this is true, then you can show that you don't have to do all the 4 axioms. Okay? So, the proof of which also you can try, otherwise we can do it in the tutorials. Okay, so the proof. Now, we define what is called normal subgroup, or it is also called invariant subgroup. If H is a subgroup of G and GIH, the left coset, is equal to right coset for all GI in G minus H, then H is called a normal subgroup or an invariant subgroup. So, what is a normal subgroup? It's a subgroup for which left coset will be same as the right coset for all elements in G, but not in H. What happens if I take an element in H? Since H is closed, the coset will be H itself. You cannot generate a distinct element. Okay? So, if this condition is satisfied, left coset is same as right coset, then we call it a normal subgroup. Further, we can define what is called factor group or a quotient group. This can be defined for normal subgroups. Let H be a normal subgroup of G, then we define this as G quotient H is equal to H G1H, G2H, etc. some GMH. Okay, I can always write G in terms of this, right? We have written already this one when we talked about Lagrange's theorem. So, we can write H and distinct cosets of H and all its distinct cosets. I am writing with left coset here, you could have written with right coset, because since it is a normal subgroup, it's both are same. Okay. This set of sets is itself a group. This set of sets is a group. What is the operation? The operation is the following. What is the binary composition? So, GIH multiplied by GJH, because here 2 elements are 2 cosets, remember. Okay, this is equal to GI composition GJ. This is another element, right? That element, take the coset with that element. Okay, now you know this, if you take any 2 elements here, compose them like this, third element also will be in the same set. So, like that you can show all the group axioms. What is the identity here? This has to form a group, that means there should be an identity. What is the identity? If you have the identity, you should have E here, right? So, EH is what? H itself. So, in this group, identity is H. In this set of sets, identity is H. And inverse, for every GIH, there will be a GI inverse H. Correct? For GIH, there exists GI inverse H, such that GI H multiplied by gi inverse h is equal to gi inverse into h, which is equal to h. This is E. So that is equal to h. So inverse also exists. So we have shown all the group axioms. Associativity is a kind of import of associativity of G, closure, identity and inverse. So this itself is a group. This kind of a group is called a factor group or a quotient group. Let's look at a simple example. We have considered a set of all integers under addition is a group. Set of all integers under addition is a group. Now let us define H as set of all integers divisible by 3. Let's take set of all integers that are divisible by 3. What is this set? This set is equal to minus 9, minus 6, minus 3, 0, 3, 6, 9, etc. These are all divisible by 3. Is this a subgroup of this under same addition? It's a subgroup, correct? So H plus is a subgroup of Z plus. Now, since it is an abelian group, it's also a normal subgroup, because you add any element from left or right, it doesn't make any difference. So it's also a normal subgroup. It's also a normal subgroup. Now, what are the elements that are in Z but not in this? There are many elements, but let me take 1 is not there, so I can write a coset with 1. So 1 plus h is equal to minus 8, minus 5, minus 2, 1, 4, 7, 10 and so on. This is not a group, but this is a coset. Okay. Now let me take 2 plus h. This will be minus 7, minus 4, minus 1, 2, 5, 8, 11 and so on. What will be 3 plus h? 3 plus h will make this minus 6, minus 3, 0, 3, 6. It is same as h. Notice that 3 plus h is h. Okay, so I will not get any new. Now if I can write this z, I can write this z over h as h comma 1 plus h comma 2 plus h. The entire integers can be written as h 1 plus h 2 plus h. Okay, now this is a 3 element set. It has to be a cyclic group. Any 3 element set is a cyclic group. This is like h, 1 plus h, 2 plus h, 3 plus h is same as h. This is called divided by h, where h is given as integers divisible by 3. So it is a 3 element group. It's a set of sets. Each set is an infinite set, but the factor group is finite. So many times in physics, we use this trick. We have, for example, in crystallography, you have space groups. Space groups are point groups and translations. Translation is an infinite group.